Okay. Is everybody listening? Okay. All right. So thank you very much for your time today. I will be talking about what DWave has next coming for you. We've been working on this for a couple of years now, and it's pretty exciting to finally reach the end of this development cycle and be able to finally be able to talk about it. So today, my talk will be split into two parts. The first part, I will just go over the previous technology, the DWave 2000Q tech, and I would like to talk a little bit about this new feature that we have released a month ago or 2 months ago. Just want to make sure that you are all aware of it. And then I'll dive right into the next generation platform. Okay. So the DWave 2000 qubit was released a few years ago, and at the time, it was one of the most complex superconducting electronic systems that had ever been made. And here I have some numbers just to highlight a little bit of the actual complexity of the system. And for the next generation system, we're scaling all those numbers quite significantly. So we will have over 1 million Josephson junctions. We will have over 80,000 of flux decks and over 20,000 QFP shift registers. So quite a significant scaling. What's not really changing between the two generations is that the next system will also implement the transverse field Ising model. Okay, so if you have been using the DWave 2000Q or the 2X before that, or the DWave 2, you are probably very familiarized with this plot here on the left. That's the annealing schedule of the system, and it just shows the two driving signals that control the quantum annealing. So throughout the history of the system, all you could really do to change the annealing schedule was to make it slower or make it faster. So you could change the timing of it. But throughout some internal research and also through collaborations with some of you, we realized that by changing the annealing schedule, you could actually yield some really positive results. So we've done some serious research and developed some new features that would allow users to have more control over the annealing schedule. And some of those features are listed here. The first one we released was the anneal offsets, which allows you to add on a per qubit basis, a little offset. That means that some qubits will anneal before and some other qubits will be a little bit delayed during the annealing. The next feature was the anneal pause, which means that you start the annealing and then at a certain point in the annealing, you can stop the two drivers and hold that level for a specific amount of time, and then you can continue and conclude the annealing. After that, we introduced the anneal quench, which, as the name implies, you can start the annealing and abruptly you can conclude the annealing as quickly as possible. Right now, 1 microsecond is as fast as you can go because of I/O limitations. And last but not least, we introduced reverse annealing, which opened up the doors for a completely new type of quantum algorithm. And some work like the one presented by Andrew this morning would not be possible without reverse annealing. And in reverse annealing, you can initialize the system in a specific state and run the annealing backwards. So you start with the transverse field driver really low, and you start raising the transverse field up to a certain point, and then generally you just quench the system after that. So today I'm talking about this new feature called age gain. So age gain is a new time-dependent control that you have that allows you to apply a local bias, so an age bias to all the qubits in the processor at any point during the annealing. So what it does is it changes the Hamiltonian of the system a little bit, so we get that GT term there. It is a PWL signal, so you have up to 20 points that you can choose to create this waveform. And you can set the values just to anything between plus and minus 5, so in age units. So some of the cool things that you can do with this new feature are shown here. So for example, you can run susceptibility measurements on the processor, the same types of measurements that are described in the phase transitions paper. You can also run quantum tunneling experiments on the processor. So here is a waveform showing you how this feature works. So the upper part here is just really showing you the regular annealing waveform. So you start from in the beginning of the annealing with s equals to 0, and you anneal up to a certain point in s, and then you hold, and then you quench. So we're using some of the new features there. And then for G remains as 0, and then at some point in the annealing, you can specify G to be either plus a value or minus a value, and that's how it works. So it's pretty simple. You get 20 points, it's a PWL waveform, and we think you will be able to do some really interesting experiments with this. If you are interested in quantum simulation of materials, you most likely will be looking forward to use this. So that's all I wanted to say. Next, I'll talk about the next generation platform. So throughout the history of DWave, I think that this new product is the first one in which the design was mainly driven by feedback that we received from users. So you told us your success stories, you told us what you needed, what was not good, and we listened to that, and we tried to come up with the most useful platform that we could possibly conceive, and that's what it is. So the three main things that people requested were that they wanted more qubits, they wanted more connectivity, and they wanted less noise. So for the next generation processor, we're giving you more than 5,000 qubits, okay, so you can solve larger problems. We're giving you more connectivity, so that means you can pose more complex problems. You will be able to reduce the chain length of your embeddings. So the qubits are going from a degree 6 to a degree 15. So that's a 2.5 increase in connectivity right there. And we're also lowering the noise of our processor. There are many sources of noise, and we try to tackle all of them, and we managed to mitigate many of these sources of noise. So lowering the noise means that now you can specify the problem that you're actually trying to solve more accurately. Because noise affects that precision that you can actually specify the chip and specify the problem, and if you're solving the wrong problem, you'll be getting the wrong answer. So it makes perfect sense to lower the noise of the chip. So first, I will talk a little bit about this new architecture. Chimera is no more. Okay, the new architecture is called Pegasus. And here I have two pictures. One of the Chimera, the DWave 2000Q that you are familiar with. And the other one is the Pegasus, really nice and colorful. It's really pretty. And here at the bottom, I have some numbers just to highlight the actual scaling that we're getting in this processor. So over 5,000 qubits, over 40,000 couplers, and 2.5 increasing in the degree of the qubit. So if you look closer to this new architecture, over here I have the regular Chimera unit cell, right? You have 8 qubits, and you have the internal connectivity that you are used to, and the external couplers. Here in the Pegasus picture, here I have 8 qubits as well, and all the connectivity you get in the Chimera is still there, but as you can see, we added way more couplers. So one of the things that I have to say is that we don't expect people to easily get used to the new Pegasus architecture. So we don't want to wait until the system is online for you guys to have an opportunity to play with this new architecture. So if you go to this website, oceandwavesys.com, you can download the Ocean API, which is this open source API developed by DWave. And in it, there are multiple tools already available that allow you to start playing with this new architecture. So you can start porting your Chimera problems into the Pegasus architecture. You can see what kind of benefits you get from this new architecture, from the extra connectivity. And there's a simulator of the topology and all that. So if you want to be ready for when the system is finally online, then you can already start getting ready for it. Here I have another slide showing a couple of examples of basic embeddings. The one that I like to highlight is the cubic lattice. In the Spinglass paper that was published in Science, the work was done on a cube with 8 by 8 by 8 spins. and the maximum chain length for that embedding was 4. So if we were to run the same kind of problem on the Pegasus architecture, or on the P16, our next generation product, we would be able to embed a 15 by 15 by 12 cube, and the chain length would be reduced to only 2. So that's a pretty significant increase in the. It could yield a significant increase in performance right there, just because of the lower chain lengths. The next thing is noise. So we worked really hard. There was a lot of research and development done to achieve this, and we lowered the noise of our processor. And that means that we are expecting to have much more precise control of the annealing parameters, because we will get a more accurate calibration. We'll have more multi-qubit tunneling, and this is perhaps my favorite, because I spend a lot of time calibrating these chips, faster calibration. So it makes me really happy that we can get that. So just to give you an example of what the new fabrication, or what the new processor will look like, here I have 2 data sets, okay, comparing 2 DWave 2000 qubit processors. And if you're not familiarized with this measurement, what I'm showing here is the single qubit tunneling rate. So there are 2 peaks, and what this means is that for one peak, I'm initializing the state of the qubit in one ground state, and then seeing how long it takes for the qubit to tunnel to the other state, to the other ground state. And so what we're looking for here is sharper peaks. So if you have sharper peaks, it means that you have less flux noise in the system. So comparing the 2 data sets, the red is the standard DWave 2000 qubit processor that has been around for a while, and the blue is the new DWave 2000 qubit using this lower noise technology that we have developed. So as you can see, based on this width, which gives us a quantitative value of the flux noise in the system, we get roughly a 5 times decrease in the noise. So that's a really good, exciting result. If you want to know more about that experiment, and if you want to know more about what lower noise will do to your problems, and what kind of benefits you'll get from it, there are 2 white papers on our website that detail the experiment I just talked about, and it also talks more about multi-qubit tunneling experiments. And there is this other white paper here that shows you how the lower noise technology improved the performance of the spin glass problem that we published last year. Now, if you don't want to just read about it, and you want to actually try to use the lower noise processor, you can go to our cloud service, Leap, and you can get access to it right there. We have both processors still available, so you can still compare between the standard 2000 qubit processor and the newer lower noise processor, and see what kind of benefits lower noise can bring to your applications. So the last thing I want to say is it's software related. Okay, so we believe that the quickest way that we will bring value to our customers is by making it easier for them to build these hybrid applications where they take advantage of the quantum resources and they take advantage of the classical resources, put them together, and we think that they will get value from that. So we are spending a lot of time redesigning the entire infrastructure around our processor. So it is faster for you to send your jobs to the chip. It is also faster for you to get data from the processor. So we're targeting an overhead of less than 50 milliseconds, plus the time that you actually spend solving the problem. And we are going to be introducing this new feature called block scheduling, which allows you to get dedicated access to the system. So you will be the only user during that period of time. So nobody else can send jobs to the chip while you have exclusive access. So that's all I had. I just wanted to say HGain is available right now. You can get access to it. Lower noise, DWave 2000 qubit, it is also available right now, and you can start playing with it. The hybrid applications environment, we will have an announcement in 2 days, I'm spoiling it, that will make available lots of features for you to start using right away as well. You can download Ocean and start playing with the new architecture. So we are already making available lots of these features so you can start getting ready for when the chip shows up. And we think that by mid-2020, that's when we're finally going to release this new system. Thank you very much for your time. That's all I have for you.
You mentioned that when you were talking about this H-gain scheduling and some of the other anneal scheduling parameters, sort of that you had some degree of control, 20 data points basically in this linear schedule,
Right.
point-wise schedule. Is there any work being done to implement arbitrary, low-level control over the dynamics of the system? I mean, IBM just came out with this open pulse architecture, and so you can do everything from a very analog point of view.
Well, it depends exactly what kind of level control that you want. Usually we develop these features based on user feedback, and they say, oh, we need this kind of control, and then we find a way of making that available in a reliable way, right? But right now, I think this is the last feature that we will be releasing for the DWave 2000Q processor. There's nothing really in the pipeline for anything before we release this next system. But if you have any requests, we can talk about it, and I'll be glad to give you a better answer. Yeah.
I think I understand the H-gain, what the H-gain is, but may I ask, what is the situation where this H-gain is a powerful tool to investigate the system?
In what kind of situation?
Yeah.
Well, if you're trying to measure the susceptibility of the system, you need the H-gain. If you're trying to run this exact measurement that I specified here, you need something like the H-gain. You need the control of the applied field of the qubit. So, yeah, I don't know if that's enough. It's not a feature that will help for every kind of problem solving, right? There are situations that it would be useful. There are certain experiments that you can run that you would be useful.
Okay, thank you.
It's a small comment. We have an example in which the H-gain feature accelerates reverse annealing explanation.
Oh, okay.
Yeah.
I have a question. Here.
Oh, sorry. Oh, okay.
Two questions about hardware, one question about the software.
Okay.
Can we have more number of anneals per call? One. And the second question about the hardware is how much precision increase per bit we have on this new couplers. Currently we have 4 bits on each part, 5 bits total.
Okay.
How much? What is the number? What is
I have to get back to you on the second question because I'm not sure.
Sure.
And the first question is no. You don't have currently you don't have
so nobody asked
any way
you
of
for more calls, right?
more annealings
More
per call.
annealings
So you
per
anneal
call.
multiple times
Yeah.
before reading the state of the
Currently we
qubit.
have 10,000. We need more, right?
Okay.
In some applications, like the application that I'm talking about.
Okay.
And then on the software side, chain break strategy is really, the default one is the system basically solves the problem, the software.
Right.
And the other one, majority vote, is not really a very good strategy. Is there going to be any other improvement on that part?
On the hybrid. I think some of these questions might be answered by this announcement on Monday.
Okay.
There's not much I can comment on that right now.
Okay.
But,
Sure.
sorry. Yeah. All right. Thank you.